Hello guys, welcome to Technorec. Welcome to the first video of the playlist learning algorithms in JavaScript, right? So there is a prerequisite to know at least some level of JavaScript in order to proceed with the video. I mean, it would be very good if you know JavaScript, some level of JavaScript, and if not, you can learn JS from any of the videos. There are a lot of videos on the internet on YouTube, and you can learn and get some understanding of JavaScript from those videos and come back later in this video and learn this algorithm. So we would be learning binary search algorithm in this video, right? So let's start. So what is binary search? So why do we call this algorithm binary search, right? And the first thing, apart from binary search, let's try to understand what is an algorithm. Algorithm is a set of instructions, like instructions to do some task in a more optimal way, right? So what is an algorithm? Algorithm, a set of instructions to do some task in an optimal way, right? In an optimal way. So that's what we would do with the code. So in coding world, an algorithm is a set of lines of instructions to solve a problem, to write some code in an optimal way, right? So binary search is one of those algorithms. So why do we call this algorithm binary search? So binary means 2, right? Binary means 2, and search means to search something, right? So what do we mean by that? So the meaning of this is like this is an algorithm which is categorized as divide and conquer, right? Divide and conquer, right? This is what politicians do. They divide and then conquer, right? I'm just joking, for context. But yeah, this is what we would be doing with this algorithm. We would divide and then conquer, get a result, right? So in a straightforward way, what it does is it divides and gets the result from the data we give to our functions, right? So let's say, so basically for binary search, there are two conditions. In this video, so we would be working on an array which would contain ultimately some numbers, and the other condition is the array should be sorted, right? Sorted means it should be sorted in an ascending or a descending order, right? Okay, so there are two conditions in order to work with binary search. So let's move ahead with the binary search algorithm. So what it does is, let's take an example. Let's say we have an array of 1 2 3 4 5 6 7, right? And it is sorted, if you see, right, in an ascending order. Okay, now there is a target number that we need to search for, which is, let's say, 6. We need to search for 6. Okay, we need to search for 6. Now, how we would be proceeding? So we would be proceeding like, let's say, what are the fundamentals of binary search? It says divide and conquer, and in binary, divide in 2, always divide in 2. Let's take 2 indexes, right? Let's call it start and let's call it end, right? There are 2 indexes. So what we would ultimately be doing is we would be dividing this array into 2. So how can we do that? So we have to find the middle index of this array, right? The middle index 0, 1, 2, 3, 4, 5, 6. We have to find the middle index of this array. So how we would be doing that? 0 plus 6 by 2, which is 3. So what is the middle index? This is the mid index. This is the mid index of this array. So what we would be doing is, now we have start, which is equals to 0, end, which is equals to, which is array dot length minus 1, means end of the array. I mean, let's call it last element of the array, rather. Last element, yeah, index of the array, right? Okay, now the mid is, which is 3, and this was 6, right? So what have we done? Now let's say our element, now let's write an algorithm. Okay, so there are there could be multiple conditions in order to find our element, right? So we have divided our array into 2. Now we have an array, you can look at it. Our mid is here. Here is a mid. So we have this array. Okay, start is 1, end is 7, mid is 4, right? Now what we would be doing is, we would be searching in our element across from left to right, right? So what we would be doing is, we have the mid, right? And our target is 6. What we would be doing is, we would say, and our mid is 4, right? So what we would be doing is, we will say if array mid element it's equal to a target. If it is, then we will return true, right? Let's say our mid element is not equal to the target. Let's say if mid array it's less than the target. So what does it signify? If our mid element is less than the target and our array is sorted, so what it signifies that our target lies, our mid element is less than the target, right? Because let's put the target at one place, and let's imagine like our mid element is less than the target. So what could happen? Our array is sorted, so we can say that our target should be lying, so our array is sorted, right? Okay, our array is sorted and our mid element is less than the target. So what can we say by seeing this condition? We can say that our target could be lying right side of the array, right side of the mid element, could be lying at the right side of the mid element. Our mid element was 4, okay, and our target was 6, and our mid element is greater than the our mid element is less than the target. So target lies on the right side. So what can we do is, we can shift our start to mid index, whatever it is, plus 1, right? And we can keep the end as same, and we now have a new mid. New mid is start plus end by 2, whatever it is. Okay, now we can see that our start, end and mids are changed. Our end is same, start is changed, mid is changed, because mid depends on start and end, right? So now we can see that we are so close to our target element now, because our start is at 5, okay, and end is at 7, and our mid could be this. Now our mid element would be, now if mid would be equal to target, so return true. Okay, now you get it, right? How do we find our target element in the sorted array? By using binary search. So let's get to the code. Let's try implementing this algorithm, right? So I've already implemented the algorithm in two ways. Let's go through them one by one. So there are two ways to implement that algorithm. Okay, so let's talk about time complexity of this algorithm. Why do we use binary search? Because you heard, like I said, what is an algorithm? Algorithm is a way of writing code, writing some instructions in an optimal way, solving a problem in an optimal way, right? So this is an algorithm, some instructions in an which solves a problem in an optimal way. So for optimal way, this must have for solving the problem in an optimal way, this should have some time complexity, right? So what is the time complexity? So you see the time complexity of this algorithm is O of log n. So I would go through this time complexity concepts in deep in another video. Just we can keep that for another video. But for now, let's just consider this as like O of log n signifies how fast our code runs, right? Or how slow our code runs. Okay, just log n, because n is always greater than log n. Log n is smaller than n, right? Log of some number makes it small. Okay, let's move ahead. And space complexity. So talking about space complexity is how it signifies how much space our algorithm takes, how much space our algorithm uses. So we would be, so for binary search, the time complexity and space complexity are of log n, O of log n, and O of 1 respectively, right? Okay, why of O of 1? Because O of constant, because it doesn't uses some extra space. Extra space means using extra data structures, like extra objects, extra arrays. So we would not be using in our implementations any extra data structure, any extra arrays, extra objects or so, right? And for time complexity, it runs in O of log n time, right? So now let's get to the implementation. So let's talk about the binary search algorithm implementation in a recursive way, in a recursion. I will also go through the concept of recursion in another video, okay, in detail. But for now, let's consider recursion as when a function calls itself, it is called recursion, right? When a function calls itself, it's called recursion. Okay. Now, for the sake of code readability, just you should always try to name our functions as semantic as possible, as meaningful as possible. So you should not always add comments to your code, right? So for binary search recursive, what we are doing here is this function takes an array. Array means some array of numbers, right? From which we would find a target, right? And we are given to find a target in this array, right? So let's forget about these three for now, start, end. But for now, let's just assume that start always would start from 0, as we have already seen from those explanations that I gave, and end is at currently last index of the array. Okay, now as we already seen, what we do is we find the mid of our array, right? So why we have done math.floor? Because let's say if your array is array length is odd, the mid could be easily found. But if your array length is even, right, your start plus end divided by 2 would be some float number, right? Could be some decimal number. So let's convert that into some integer with greatest integer function. Okay, with math module which JS provides, thanks to JS. Okay, now this is the breaking condition. Why we have put this here? Okay, why we have put this here? If start is greater than end, return false. I would tell you, I would explain you about this, but let's just assume we have calculated the mid. So what this function will do, let's say this is the first condition, because you must already be getting it why I have written this. So we are checking if array, if mid, whatever the mid element we have calculated above, if this equals to target, we get the expected result. We found the element, just return true. Okay, and as I explained in that walkthrough just before now, because just before now is because if array mid element is greater than target, so what does it signify? If the mid element is greater than target, right? So you see, if the mid element is greater than target, it signifies that our target lies on the left of the mid element, current mid element. Our target lies on the left of the current mid element. So what we are doing is we are calling our binary search recursive function again with the new set of data. You see the same array, same target, the start is same because it lies on the left of the mid element. So end is supposed to be changed, right? The end index is supposed to be changed. End is to be shifted from the last index to one index less than the mid. Okay, the new mid is calculated accordingly. Okay, now what we're doing is, so this is not needed. If you see, because start and end depends on start and end depends on start and mid element depends on start and end. So we don't need to pass mid to this recursive function. So let's talk about the else condition. So the else condition would only be triggered when these two conditions are not met. So let's say the mid element is not equal to target, mid element is not greater than target, and mid element now is less than target. So now this condition would be triggered. So when the mid element is less than target, you've already seen in the walkthrough I gave, like, where should be our target. If the mid element is less than the target, so our start should shift, right? Our start index should shift. Our mid element is less than the target, our start should shift to the right because our target is on the right. It's if our mid element is less than the target, so it signifies that our target is on the right. Okay, now binary search, we are calling binary search recursive again with the new set of data. Now our start is mid plus one index more than the mid. Our start is changed, or our end is fixed, right? So we would be calling this binary search recursive function again and again and again until we found our element, until this condition is met. And whenever this condition is met, our function exits, our function stops running, right? Because we are returning the final data. And now let's see what happens if I remove this condition. So why I have kept this condition, I would tell you in a bit. Let's just call it. So we are calling our binary search recursive function with some set of data which is 1 to 10, and our target is 10. Now let's try compiling that. Node, okay, algo, which is binary search. Okay, now it is returning true, right? It is returning true because we found the element, right? Let's add some element which cannot be found, right? So what are you seeing? This is failing when we have given 11 because it cannot find the 11. It cannot find the 11 in this array, and it keeps calling this binary search recursive function. It keeps calling the binary search recursive function, right? And it is not able to exit from this function because in order to exit from this function, the element should be found. and it is not able to find the element. So it is not able to exit this function. It keeps calling this function and it gets stuck in a call stack loop. I would tell in another video like what is a call stack. It is a it can be the subject of another video, but let's for a sake, let's just assume that it has reached, it's stuck in a loop, right? It is stuck in a loop. So it keeps calling that binary search recursive function, and at the end it gives up, right? It gives up, the call stack is full, and it throws the error, the range error, maximum call stack size exceeded, right? So we should give, in such cases, we should give some exit condition. This is specifically in the case of recursive functions, like we should give some exit condition. Okay, so this is an exit condition. So at one point, you imagine what would happen. Either what we would do is we could keep shifting start to the end, or we could be shifting into the start. So what would happen is ultimately start at some point start would be greater than end if the element is not found. So what we would do is, ideally this should not be happening, right? This is not the ideal case. What we would be doing is, we would be telling our function like whenever the start is greater than end, just return false, exit the function, right? The function would be exited, right? Now if you search for 11, you're getting false. You didn't found the element and it is returning false. Okay, cool. Now let's just also see how you can write the same piece of algorithmic code in a non-recursive function in an ideal situation that most of you would be writing the functions, right? So what we are doing here, we are just, this is the more simple code than this one, but this is more cleaner. Okay, now what we are doing is, this function is taking array and the target element, right? It's same, and we are defining start as 0, end as whatever the length of the array, the last element of the array. And in the while loop, what we are doing is, it is the same condition that we had put in our last function. This is the same condition. You see, it's kind of an exit condition for this while loop, because we have to prevent this while loop. We have to add some exit condition in this while loop so that it doesn't goes in an infinite loop, right? Okay, now we have whenever the start is less than equal to, until the start is less than equal to end, the start is not greater than end, and you can write it. This is the wrong condition, right? Whenever start is greater than end, this loop will not run. This loop will exit, right? Whenever start is greater than end, this loop will exit, right? But this loop will run until the start is less than or equal to end. So for every loop iteration, what we are doing is, we are calculating the mid is same, right? Start plus end by 2 method floor, and we are checking the same. If mid element is the target, return true. If mid element is greater than target, what we are doing, we are modifying the end, keeping the start as fixed. So what we are modifying is, we are moving our search, we are moving our end to the left, because it's if the mid element is greater than target, it signifies our element lies at the left. And in the else condition, if the mid element is less than the target, it signifies our element lies at the right. So we are just modifying our start index. But in the end, let's say this loop iterates let's say this loop iterates over the whole array, and we didn't found our element. So it doesn't, because we didn't found our element because this condition is not met. So what we would be doing is, we would be returning false, because which signifies back like we didn't found the element, right? Let's just try running that. Okay, now with the same piece of code, now we are searching for 10. So this returns true, right? Now let's search for 11. This should be returning false. Search. This is returning false, right? Now it's working. So one more thing is, so this is O of log n, right? So what console.time does, it calculates how much time it is taking to run this function. So this is console.time. It starts from here. It starts a counter from here at and it ends the counter in here, right? Let's just try seeing that how much this function takes from the top to bottom in order to run this function, how much time is utilized. You see 3.6 milliseconds. This binary search function, it's taking 3.6 milliseconds, right? So let's say if the element is found, how much time it is taking. Okay, if the element is found, it is taking 3.557 milliseconds. So on an average, you can say it is taking around 3.5 milliseconds in order to run. So the recursive function should also be taking on and around same time, because the function is same, the algorithm is same. It runs in O of log n time, where n is the length of the n or length of the array, right? Let's try seeing that too. Okay, let's uncomment that code. Okay, let's just try seeing that. What should be, so it is also running on an average around same 3.3 milliseconds. Just hit again, 3.4 milliseconds on an average. So on an average, this doesn't make a difference you write the code in this way or you write the code in this way. The algorithm time, the time in which the program runs would remain almost same. It doesn't affect the program time complexity, space complexity. It doesn't affect the code, just way of writing the code to maintain some cleanness, right? So okay, thank you so much for watching this video. Hope you have learned something, and please support me and subscribe the channel if you like the video, and I would be adding more videos in future in this playlist. So thank you for watching.